This video continues a demonstration of the Configurable Custom Logic, or CCL block, on an ATtiny Series 2 microcontroller, the 3226. I'm going to pick up right where I stopped my last video, so this video will make no sense if you haven't seen that one. I strongly suggest watching it first if you haven't already. Link below. Today's subjects are the filter synchronizer and edge detector blocks. This video requires some background knowledge. I'm going to assume that you already know what a D flip-flop is and how it works with a clock. Here's our ATtiny CCL block diagram. Our first focus is the filter synchronizer block highlighted in red. The 3226 datasheet states that this block's main goal is to address glitches, which are undesired deviations from expected signal levels. Glitches can happen with combinational logic. For example, this exclusive OR might glitch down if both inputs don't change at the same time. The input will be an ATtiny pin, let2 in0 pin PB0. We'll feed it from my ATALM2000 acting as a signal generator. See link below for what an ATALM2000 is. Initially, we'll bypass the edge detector and send the filter sync block output straight to an external pin, let2 out pin PB3, so we can view it on an oscilloscope on which we can also view the signal from the ATALM2000. Our CCL input signal from the ATALM2000 will be a 250 Hz square wave to which I can add glitches. Our smallest glitches will be 1/10 of a millisecond wide. All the gray boxes in the CCL require a clock. We will get it from a square wave generator separate from the ATALM2000. We will feed it to CCL let2 into pin BB2. We will usually use a 5 kHz clock, but we'll change it to demonstrate some interesting things. Here's a quick system diagram. The ATALM2000 injects a square wave with optional glitches into pin PB0. A separate square wave generator provides the CCL clock on pin PB2. We use an oscilloscope to view both the input from the ATALM2000 and the CCL output on pin PB3. Here's a zoom in on the filter synchronizer block showing our input, clock, and output. You can see it contains an exclusive OR, a mux, and 4 flip-flops. Going forward, I'll say flop for flip-flop. To start, we will use the block in synchronizer mode. In this mode, only the first 2 flops are used. The output of the second flop leaves the block via the mux. These 2 flops make up a standard dual flop synchronizer. Here's a rule to remember. Whenever an asynchronous input signal connects to a flop, it's best to also use a second flop. This is also true for an input signal associated with a different clock. The reasons for this rule include something called metastability. It's a relatively complicated topic, so I won't go into it, but I'll put a link to a video below. So, the synchronizer helps to avoid metastability, but does it get rid of glitches? It can, if they are shorter than the CCL clock cycle and occur away from a CCL clock rising edge. This means that the synchronizer alone probably won't eliminate all glitches. Let's take a quick look at the software. This is the same file as in the previous video, so I won't spend too much time on it or look at the whole thing. And I'll also only look at this once during this video because we're only going to change a couple of parameters, and it's pretty simple. So we're using logic 2 or let2 as we did before, so we first have to set that to true. And then we set input 0 to be an input pull-up. That's the pin in 0, PB0, that the input's going to come on. And then input 1 we're not using, so it's masked, as explained in the previous video. Now this is interesting. Input 2, even though we're only using it as a clock, does have to be declared as an input. I've experimentally determined this, but the datasheet says that when input 2 is also used as the clock source, it will be treated as a 0 all of the time in the truth table. So it should work, and experimentally does. So the truth table value is 2, which is just making the input on input 0 equal the output, or the output equal the input. And now this is new. We have to set the clock source, and we're setting it to into the PB2 because we want an external clock. We could set that to clock PER, and that would be the standard peripheral clock in the ATtiny. And there are some other choices you can read about in the documentation. Now the filter, the thing we're going to look at first, can be set 3 different ways. It can be disabled, as it is now, so it's totally bypassed. Set to synchronizer, in which case just the first two flops are used, the dual flop synchronizer, or set to filter, in which case all of the flops are used, the synchronizer followed by the two flops that do the filtering that we'll talk about later. So those are the three choices. And then for the edge detector, you just enable it or disable it. But if you enable it, you really should have the filter set at least to synchronizer, if not filter. I don't think it can be used to disabled. That would be unwise because you're sending data to a clock domain. And then the sequencer we talked about last time, so we're not using it. The output is turned on, even so we can see it on the oscilloscope. Call logic to init after all of this. CCL still not running. Go down to setup, call this function, and then logic start, and then we're going. So the first thing I want to show you is a situation where the filter and the edge detector are both disabled. And this is just to get a baseline of what the input and the output signals look like. So we'll do that next. Okay, we're running, and the software is set to disable everything. So the synchronizer filter is disabled, and the edge detector is filtered. Essentially, everything's disabled. And on the lower left, you can see the board, and next to it, right here, is a clock generator that's being used to produce the CCL clock, and that's set to 5 kilohertz right now. In the oscilloscope, the yellow trace is the input, and the magenta trace is the output. So now I'm going to go over to Scopy over here, and this is the Scopy pattern generator. It's used to be able to produce digital patterns in time. So right now it's set to produce a square wave, 5 kilohertz, with no introduced glitches. And so if I run that, we'll go back to the oscilloscope, and we can see now that the output in magenta is matching the input perfectly. And in fact, if I zoom in the timescale, we can also see that there's really negligible delay. This is basically just a pass-through of the digital signal at this point. So the next thing we should do is turn on the synchronizer. So I'm going to do that off camera, and we'll be right back. The synchronizer is now on, and we immediately see two things. Let's zoom in a little bit in time. And we see first that the output signal is delayed a little bit with respect to the input, and also that we're seeing a bunch of jumping around of the output, sort of edge jitter. And I think we need to explain that before we go any farther. So let's take a look at that. Our 5 kilohertz CCL clock is slow. Its rising edge can miss an edge of the input signal by just a little. It then fails to latch the new input state for up to 1 CCL clock cycle. And keep in mind that the CCL clock generator and the ATALM2000 are separate devices. Their clock frequencies won't exactly match, so there will be a never-changing phase relationship between their clocks. I wanted this because it's realistic. It's the reason I did not use the ATALM2000 to also produce the CCL clock. The combination of the slow CCL and the ever-changing clock phase relationship explains the jitter of the output edges on the scope. They can be off by up to almost 1 complete CCL clock cycle. This suggests that we could reduce the edge jitter we see by increasing the CCL clock frequency. We're back at the running system, so now let's try increasing the CCL clock and see if this jitter reduces. So I'm going to gently reach over here and press this frequency up and hold it down, and it'll start increasing the frequency faster with time, but watch the oscilloscope and we should see less and less jitter as we go forward. Look at that. It's kind of working. Let's go all the way up to 150 kilohertz, the most this can do. And you can see that the jitter is greatly reduced. Is it gone? Let's go in this way. It's not gone, it's just reduced, because there's still a CCL clock, and that still controls exactly at what point edges are detected. But the jitter is greatly reduced by increasing the frequency. Our 5 kilohertz frequency is kind of artificially low, but it makes it easy to see things. So next, I think we need to move on and introduce some glitches and see what happens. We're back to the running system, and the CCL clock generator is back to 5 kilohertz. So now, the way we introduce glitches is by changing the file that's being used to produce this digital pattern. So I go here, open file, and I can pick this file, and it's going to produce glitches that are, what is it, like 1/10 of a millisecond wide. So if I click here, they appear. And so you can see we have 1, 2, 3 positive glitches and 1 negative glitch. Now, on the oscilloscope, you can see, I think, that occasionally glitches are appearing in the output. I'm going to do some single captures so we can look at this a little bit more closely. So there's no glitch in that one. Now we've captured a glitch, and it's been passed through to the output. And this one has 2. But let me go again. Let's do some more single captures. And there's a glitch that's passed through, no glitch. A glitch that's passed through, no glitch. Now here, look, here's a glitch that wasn't passed through to the output. So sometimes the synchronizer eliminates them, but sometimes it doesn't. In fact, often it doesn't. And so now to actually eliminate the glitches, we have to run the filter. So off camera, I'm going to enable the filter in addition to the sequencer, and we'll see if we can see any glitches in the output. Actually, before I do that, I'm going to go to the oscilloscope, and I'm going to change the trigger to trigger on glitches on the input channel. That'll make this easier to see. So in the setup menu, let's type edge now, just go down to pulse. And now this is triggering on pulses that are narrower in time than a certain threshold. So it's always triggering on a glitch in the input. And so you can see when that glitch is passed through and when it's not, as the scope triggers multiple times. So now I'm going to do something off camera that you can't see and recompile the software to turn on the filter. So you'll hear a little beep as I switch windows, and compiling now, just changing the word synchronizer to filter in the logic 2.filter setting that we saw earlier. And now it's running, and you can see that there are no longer any glitches being passed through. So let me get back to my other window here. And what can we do that's interesting? So remember, if the glitches are too wide, the filter can't filter them out. So let's go back to the Scopy application and open a new pattern that has wide glitches. So this one here, and say import. So you see the glitches got very wide. And now they're too wide for the filter to filter out. So system's operating as expected. How does this filter work? You can pause here and convince yourself that flop F will take the value from flop B1 only when B1 and B2 contain equal values. Thus, an input signal change that persists for only one CCL clock cycle is discarded. We're back to filtering narrow glitches. And so you can see that the output equals the input minus the glitches. And so now let's turn on the edge detector by changing disable to enable in logic 2.edge connect. I'm hitting compile now, and you can watch the change on the screen. So it is now starting to load, and that's complete. And you see the output changed. Now the output consists of just a pulse in reaction to all of the rising edges of the input signal. And those pulses should be 1 CCL clock wide. So let's turn on some cursors and try to measure that. So turning on cursors, and I'm going to zoom in here a little bit and do a single capture. And our cursors are already set to a width that equals the CCL clock period. So if I slide this over, we can see that the pulses really are 1 CCL clock period in width. So that's what the edge detector does. Whenever it sees a rising edge of the input signal that isn't a glitch, because of the filter, it produces an output pulse, 1 CCL clock wide. So that's the edge detector in a nutshell, working as expected. This diagram shows how the edge detector works. The output is high only when the input is high, and the input on the previous clock was low. That's all for this video. We've seen the CCL synchronization/filter and edge detection blocks. Perhaps my next video will discuss how the CCL works with the ATtiny event system to tie different ATtiny hardware blocks together. Thanks for watching.